In this lecture, we will examine the gross anatomy of the three types of blood vessels, which will then allow us to differentiate capillaries, arteries, and veins. So let's get started. Now, there are some very important lessons that you really want to remember from the last lecture. First, arteries carry oxygenated or good blood from the heart to your brain, to your big toe, and every part in between. Now recall that oxygenated means that the hemoglobin in your erythrocytes is loaded with oxygen. 2. Veins carry deoxygenated or bad blood from your brain, your big toe, and every part in between back to your heart. Also recall that deoxygenated means that the hemoglobin in your erythrocytes is loaded with carbon dioxide. Lesson number 3 is a new one for this lecture, and that is capillaries are the bridges that connect arteries to veins. We'll take a closer look at that connection now. So recall from last time that oxygenated blood flows from your heart to your big toe by way of an artery. Now once there, the oxygen molecules dissociate from hemoglobin and diffuse out of the erythrocyte. So where does it go from there? In other words, how does the free oxygen get into the tissue, in this case skeletal muscle, in order to be used by those cells as fuel for doing work? For example, wiggling your big toe or walking. Now, by the way, recall that this is the first part of the process we call cellular respiration. Well, you already know that the anuclear biconcave shape of red blood cells allows them to fold upon themselves and squeeze into the tiny vessels called capillaries. Capillaries are the tiniest of blood vessels, and incredibly, the real work of circulation, that is, delivering of oxygen to and removal of carbon dioxide from the tissues of the body, is carried out by capillaries. Now, because the walls of capillaries are but a single epithelial cell thick, they are the only blood vessels that allow the free exchange of nutrients and waste between the blood and the surrounding interstitial fluids. Interstitial fluid is that fluid that fills the spaces between tissue cells. So here you can see the single layer of epithelial cells. By the way, this is a nucleus of this epithelial cell, and here is another one. Because capillary walls are so thin, diffusion of oxygen and carbon dioxide occurs very rapidly across them. By the way, this space inside the capillary is called the lumen. Anytime you have a tube, like a capillary, an artery, a vein, or even a water pipe, this space is called the lumen. So you can see how a capillary is just wide enough to accommodate one red blood cell. You can appreciate now the importance of erythrocytes being able to stack together to form rouleaux, which then allow a bunch of cells to travel through the capillaries simultaneously. I absolutely love this microscopic study of skeletal muscle. First, look at these beautiful striations. Now you see the wall of a capillary here, and so this space between the walls is the lumen. We see a white blood cell down here, and here is a red blood cell. See, the lumen is just wide enough to let this guy through. Now capillaries do not function singly, as do arteries and veins, but rather as parts of interconnected networks of capillaries called capillary beds, or capillary plexi. Plexus is singular. Now, a capillary bed has several direct connections between arteries and veins. Remember that capillaries serve as bridges between your arterial circulation, always shown in red, and your venous circulation, always shown in blue. So let's take a closer look at the process. Oxygenated blood leaves the heart and travels down to your big toe. This good blood leaves your heart by way of an artery called the aorta. Now, the aorta is an artery with a very large diameter, too large, in fact, to fit into the big toe. So, as the aorta descends, we call that the descending aorta, it carries good blood to your lower extremities, and it decreases in size, that is, decreases in diameter, as it descends to the big toe. As the artery gets smaller and smaller until at the point it enters the big toe, we refer to the vessel as an arteriole, or small artery, and that's what you see here. Now the oxygenated blood then enters the capillary plexus via the arteriole. And by the way, there are many of these sites throughout the tissue. In other words, I'm showing you one as a reference. There are many plexi servicing the tissues, even tissues as small as those of the big toe. So once inside the capillaries, oxygen dissociates from hemoglobin. Now for simplicity's sake, I'm showing you only one oxygen molecule per erythrocyte. And because the capillary walls are only a single cell thick, remember, oxygen diffuses very easily and very rapidly into the interstitial spaces. So if we jump into the tissue, we see the free oxygen circulating in the interstitial fluid. Now these skeletal muscle cells want that oxygen for fuel, so the oxygen diffuses across the cell membranes, gets used up by the cells, which then generate carbon dioxide as a waste product of, remember, you got it, cellular respiration. And now the process goes in reverse. That is, carbon dioxide diffuses out of the muscle cells and back into the interstitial fluid. The carbon dioxide diffuses back across the capillary wall and back into the erythrocytes. Hemoglobin, remember that hemoglobin has an affinity for carbon dioxide as well as oxygen, absorbs that carbon dioxide, and now your blood is deoxygenated. So this bad blood flows into your venous circulation by way of these very small veins called venules. Venules then become larger veins as the deoxygenated blood ascends. So the deoxygenated blood ascends back to the heart by way of the largest vessels which carry bad blood, and they are called vena cavae. Now, by the way, it is the inferior vena cava that drains the lower extremities of deoxygenated blood, while the superior vena cava services the upper extremities, the head and the neck. Now finally in this lecture, let us compare and contrast the other two types of blood vessels, namely arteries and veins. So you know now that arteries carry oxygenated blood. You also know that veins carry deoxygenated blood. I should let you know here that there are a couple of exceptions to these rules. However, those exceptions do not concern us here in the head and neck. I just want to make you aware of them if you are studying the circulatory and respiratory systems in more detail. By the way, those exceptions concern the pulmonary arteries and veins. What does concern us here, however, is the gross anatomy of arteries and veins. So check out this microscopic survey of an artery and a vein. The artery is here and the vein is here. Question: what do you notice about these two vessels, disregarding the apparent size differential? I hope that you immediately notice the structural difference in the two blood vessels. Specifically, I hope that you notice that this artery is quite symmetrical and nearly circular. This vein, well, not so much. In fact, the vein looks as though it is collapsed, and therein lies the most significant difference in the gross anatomy of arteries and veins. So if we examine the gross anatomy of the generic artery and generic vein side by side, we see the lumen here and here. When we compare arteries and veins, we can see that they have three tissue layers in common. Now we call these tissue layers tunics, like jackets. And so we see the tunica adventitia, that's the external jacket, the tunica media, that's the middle jacket, of course, and the tunica intima, that's the internal jacket. It's the tunica media, or middle jacket, that I want to focus on here. The tunica media is composed of smooth muscle. Now remember that smooth muscle is one of the three muscle types, cardiac muscle and skeletal muscle being the other two. The tunica media is obviously involuntary. That is, you don't have to think about your blood flowing through your body. It just flows. The tunica media of the average vein is comparatively thinner than that of the comparable-sized artery. And the question is here, why? So you are familiar, I'm sure, with blood pressure. Now, all of us have had our blood pressure taken at some point in time. The doctor, the nurse, or the clinician will call it a number like 124/78. Now that top number, 124 here, is called your systolic blood pressure. The bottom number, 78 in this case, is called your diastolic blood pressure. So your systolic blood pressure represents the highest pressure exerted on the circulatory system when your heart muscle contracts. Your diastolic blood pressure then represents the lowest pressure exerted on the circulatory system when your heart muscle relaxes. These numbers are in millimeters of mercury, by the way. So your arterial circulation then must be able to hold up under the extreme pressure generated when your heart contracts. That ability to withstand the high pressure of contraction is provided by that thick, durable tunica media. And because the venous circulation does not experience the high pressure of contraction, veins are able to have a thinner, less durable tunica media. One more time. Arteries have a thicker tunica media than do veins in order to withstand the high pressure generated by contraction of cardiac muscle. And now I think it's about time to locate and identify some arteries. And we'll do that in the next lecture.